All right, 4.4.1. Today we're going to talk about the derivatives of exponential functions. Quick reminder: exponential functions are anything to an exponential power where the exponent is a variable. So some examples: y equals 5 to the x, y equals 8 times 3 to the x, or y equals, let's do 7 times to the 4x squared power. Anytime you have an exponent where the variable is in the exponent, that's an exponential function. Not the same as a power function. A power function is the other way around, like y equals x to the 8th. That's a power function because you have a power that's a constant, but the variable is on the base. Exponential functions are the other way around. Exponential functions have a variable in the exponent. One of the most famous exponential functions is y equals e to the x. It's sometimes known as the exponential function. That's because the base e can be used to model a lot of different growth equations. It's a pretty famous one that's used an awful lot. And that's actually the one we're going to talk about today. We're going to talk about how to define the derivative of that. And then we'll get into defining the derivatives of ones like these. We're going to start with e to the x. And actually what I'm going to do is we're going to look at the derivative graphically, because that's going to help us see how the derivative of e to the x is related to the original. All right, so here I've got the graph of f of x equals e to the x. So this is what e to the x looks like. And on this grapher, I'm just going to graph the derivative. I'm going to graph f prime of x. And you'll notice there's f prime of x. Again, in red, you've got f of x. In blue, you've got f prime. F of x, f prime. You'll notice they're the same function. E to the x is the one and only function whose derivative is the exact same function. So what is the derivative of e to the x? It's e to the x right again. Probably write this down. Yes, I used a u this time. Often will use a u instead of an x because that helps remind us of the chain rule. And if I've got something on the inside in that place of the u, I need to times by the derivative of the inside. So derivative of e to the u is e to the u. Straight up, same exact thing. Let's try one. Now this one's not just e to the u, that's got something on the inside, but we know how to handle that. That's just the chain rule. So I'm being asked to find f prime of x and f double prime of x. So let's get to it. F prime of x equals, all right, so my outside function is e to the something. I know the derivative of e to the something, it's just e to that same something. So the derivative is going to be e to the 5x squared times the derivative of the inside. Inside that e to the something was a 5x squared, so times 10x. There it is. If I wanted to find the second derivative, we just take the derivative again, f double prime. But now it's going to require, I've got something times something else. That's going to require the product rule. So first times derivative of the second. First is e to the 5x squared times derivative of 10x is 10 plus other way around, second times the derivative of the first. Second is 10x. Derivative of e to the 5x squared, we just did that. Derivative of e to the anything is e to the anything. So e to the 5x squared. But then times the derivative of the inside because of the chain rule. So times 10x. I could clean this thing up. Let's see. They both have an e to the 5x squared. They both have a 10. So why not factor that out? Let's factor out a 10, e to the 5x squared. I'll be left with, I'm taking both of them out there. So 1 plus, if I take that out and one of these 10s out, I'll be left with a 10 times an x times an x. 10x squared. I could write it like that. I kind of like it like that. If you wanted to factor it, you don't have to, but I like the way that one looks. So I'm going to leave it like that. All right. Now we're going to go to the derivative of any exponential function. So the derivative of a to the x, where a is some positive positive constant. I'm tripping over my words here. So for example, if I have f of x equals 5 to the x, what's the derivative going to look like? Right. So to do that, we're going to do a quick review. So just a reminder, if you have something like e to the natural log of 5, this seems completely unrelated, but it's going to lead us to how to do a problem like this. If I do e to the natural log of 5, we've got to remember that exponential functions and logarithmic functions are inverses, so they undo each other. So e to the natural log of 5 is just 5. E to the natural log of 128 is 128. E to the natural log of a to the x is just a to the x. All right, that's going to help us out. So actually, I'm going to do this one. I've got this all written down here, but I want to do it off to the side. So let's say I had f of x equal, what was my example here? 5 to the x. That's the final example. And I wanted to find f prime of x. Well, right now, I don't know how to do that, but I can use these handy rules for rewriting it. I can rewrite my f of x to be e to the natural log of 5 to the x, which seems like a horrible thing to do, but it's actually going to make things easier. The reason that's nice is there's another rule that has to do with natural logs. If I have natural log of 8 to the 4th, I can rewrite that as 4 natural log of 8. So this one, I can further rewrite as e to the x times the natural log of 5. And now we're going to take the derivative. F prime of x, well, now it's e to the something. I know how to take the derivative of e to the something. It's just that same e to the something. But then I have to multiply times the derivative of the inside. Well, the derivative of the inside is x times the natural log of 5. Natural log of 5 is just a constant. It's just a number. So derivative of x times the natural log of 5 is just going to be the natural log of 5. There's my derivative, but I can clean this up a bit. I can rewrite this thing. Again, I can use my rules and I can rewrite that as e to the natural log of 5 to the x, right? Moving that back up here using this rule up there, times the natural log of 5. And then this thing, well, it's e to the natural log of something again. That's like these here. Those e's and natural logs are inverse functions. They are going to undo each other. So my final answer is just 5 to the x times the natural log of 5. Now that seems like a whole lot of work to find the derivative, but take a look at where I started. F of x was 5 to the x. And look what the derivative is. 5 to the x times the natural log of 5. Turns out that's going to work every single time if I've got anything other than an e. So that's all this stuff here. I was just going to have it written out, but we did that. The derivative of a to the u, where a is some constant, is just that exact same a to the u, but then times the natural log of a. Let's do some practice, make sure we have it down. If I had y equals 28 to the x, what's the derivative? Well, the derivative of 28 to the anything is 28 to the anything. Exact same thing, but then since this wasn't an e, I multiply by the natural log of 28. I would try these next 3 on your own to make sure you have it down. Help maybe pause the video and give it a shot. All right, I'm going to do it now. Derivative of 3 to the x. Well, that's just 3 to the x times the natural log of 3. What about pi to the x? Same rule. That's pi to the x times the natural log of pi. What about e to the x? Same rule. Now, this is the one we learned earlier. Derivative of e to the x is just e to the x. But I can use this rule just as well. That's just a rule in general. I could say derivative of e to the x is e to the x times the natural log of e. But the natural log of e, that's equal to 1. So it's really just e to the x times 1, which is just e to the x. That's why e to the x is a special one. Derivative of e to the x is just e to the x, because when I apply this extra rule where I multiply times the natural log of e is 1. So then it kind of just goes away. All right, let's try a little more complicated one. Let's try one that's going to involve the chain rule. You might want to pause the video, try it yourself. I'm going to start it right now. All right, derivative of 7 to the anything is that same 7 to the anything times the natural log of 7, because that base was not an e, it was a 7, right? But then, I'm going to use parentheses this time for my multiplying. But then I had something on the inside. So chain rule says then you multiply by the derivative of the inside. Derivative of the inside would be 8x. Okay. At what point on the graph of the function p of t equal to 2 to the t minus 3 does the tangent line have a slope of 21? If I'm caring about when the tangent line has a slope of 21, that's the same as asking when this has a slope of 21. So I'm clearly going to have to find the derivative because derivatives tell me slope. So p of t, p prime of t, the derivative would be, well, that's 2 to the t. So derivative of 2 to the t will still be 2 to the t, but then times the natural log of 2. Derivative of minus 3, that's a constant, that's 0, so I'm not even going to write it. Okay. I care when that derivative is equal to 21 because I care when the tangent has a slope of 21. Again, derivatives tell me slope. So I'm going to just set that equal to 21. 21 equals 2 to the t times natural log of 2. All right, I want t by itself. So I'm going to divide both sides by natural log of 2. So I can start getting that t by itself. 21 divided by natural log of 2. I'm just going to put that in my calculator. That ends up being 30.2966 equals 2 to the t. This problem is a problem we should know how to solve from pre-calculus. There's a couple of ways to solve it. I'm going to go through both ways just in case you had a preference. They both work just fine, but I want to solve it a couple of ways just as a reminder of how we can solve it. All right, one way we can solve it, I'm going to call this method 1. All right, method 1 is to change into a log form. So as a reminder, if I have the log base b of, let's say, let's use a different variable, let's use a, let's say that's equal to m, it really doesn't matter what I use there. But if that was the case, you know what, I'm not going to use m, I'm going to use n just so we don't confuse it with slope. Let's say that's n. That's a log form of an equation. It can always be written into exponential form as using the same base, but it's going to be b to the n equals a. So that might be something you should, well, hopefully you remember. That's something we can change for changing something from an exponential form to a log form, right? Excuse me. So for our first problem here, for this, I'm going to rewrite it. 30.2966 equals 2 to the t. That's an exponential form. I'm kind of stuck. So when you're an exponential form and you're stuck, you can change it into a log. Changing it into a log would be the same base. So it's going to be log base 2 of my number. So of 30.2966 is equal to t. And then I can just plug that in my calculator and get it. So hopefully if your calculator has a log base 2, you can just plug it in using that log base 2 formula. If it doesn't, you can use a change of base formula. If you care, I'll do the change of base formula just because some people may not have this in their calculator. So if you can do logs with a base of 2 in your calculator, just do that. If not, you can do the change of base formula, which says the natural log of the top one over the natural log of the bottom one is the exact same thing. I can put that in my calculator and I get t is about equal to 4.921. Okay, let's do this in another way. All right, so one thing I could do is if you have a problem like that, you could take the natural log of both sides. I could rewrite this as the natural log, 30.2966 equal to the natural log of 2 to the t. The reason that works is there is a log rule where you can take that t and bring it down up front. And then I'd have the natural log of 30.2966 equals t times the natural log of 2. So then divide both sides by the natural log of 2, and you'll notice we'll get the same thing we had before. Natural log of 30.2966 over the natural log of 2 be equal to my t. So t must be 4.921. All right. So two ways you can do it. You can use your change of base formula, or sorry, you can use your changing of forms from log form to exponential form or back, or you can use your log rules and just take the natural log of both sides. Either way, you get to the same answer. All right, last problem. The spread of a flu in a certain school can be modeled by this ugly equation, where P of T is the total number of students infected after T days. And then this is going to be asking us some different questions about it. And this type of question is really making sure we understand the calculus involved. So the first one says, estimate the initial number of students infected with the flu. Problems like this sometimes catch students because they get so used to, hey, I see a problem, I need to take the derivative, that they just do that without thinking. Think about what the problem's asking for. This thing tells me how many people are infected. This question is asking how many people are infected at a certain moment in time, right? I'm not going to take the derivative. This tells me how many people are infected. I just want to know the initial number of students infected. Well, the initial number would be when my time in days is equal to 0, right? When 0 days have passed. This problem tells me the number of infected students after T days. For the initial number, that would be when no time has passed. So plug in a 0 into there. So the answer is going to be P of 0, which would be 100 over 1 plus e to the 3 minus 0, which is just 3. I could put that into my calculator and I could get an estimate, 4.743. All right, one important thing to note. A lot of people correctly recognize that I can't have 4.743 students. That's not possible. So if I was to give my best estimate for the initial number of students infected, I'd probably say 5 students. Now, on the AP exam, we always want to be accurate to 3 decimal places unless it states otherwise. So if this question said estimate to the nearest student, then I would say 5. But if it doesn't say that, I'm going to go ahead and leave it as 4.743 because I can't go wrong by having that accurate to 3 decimal places. So in calculus, unless it says otherwise, always be accurate to 3 decimal places. All right. How fast is the flu spreading after 3 days? It's asking how fast the flu is spreading. That's a rate. So that's going to be a rate of change. That's going to be slope. That's where I need my derivative. So in order to answer that one, I first need to find P prime of T. All right. It's written like this. That's a quotient. It's going to require the quotient rule. I'm going to actually do that off to the side here. I don't know that I can fit it in here. Well, maybe if I get it small enough, I can. I'll try. All right. So my function was 100 all over 1 plus e to the 3 minus t. So my derivative P prime would be low d high. Low is 1 plus e to the 3 minus t times the derivative of the high. Well, the derivative of 100 is 0. So that whole term is going to go away. Minus, so low d high minus high d low. So 100 times the derivative of the low. All right, well, the derivative of 1 is 0 plus derivative of e to the anything is e to the anything. So e to the 3 minus t times the derivative of the inside, because I've got a inside function there. Derivative of 3 minus t would just be -1. So times -1. I'm just going to put the negative right here. And then all over low squared. So all over 1 plus e to the 3 minus t, that whole thing squared. All right, let's simplify this out a bit. That, again, is, of course, going to be 0, so it's gone. Here I've got a negative times a negative is a positive, so it's really going to be a positive 100 times e to the 3 minus t, all over 1 plus e to the 3 minus t, that whole thing squared. All right. Particularly, I cared about how fast the flu is spreading after 3 days. So really, I want to find P prime 3. So I'm just going to plug a 3 into there. That'll be 100. E to the 3 minus 3 is 0. That's convenient. all over 1 plus e to the 3 minus 3 again is 0, all squared. I said it was convenient because you should hopefully remember your rule. Anything to the 0 power is 1. So that's really just 100 times 1, which is 100. All over 1 plus 1 squared, which would be 4, because 1 plus 1 is 2, 2 squared is 4. 100 over 4, that's 25. Now I got to think about this unit. That's going to have a unit. That's how fast the flu is spreading. This original function gave me the students, right, and over a number of days. So that's going to be 25 students per day. That is a very worrisome rate of spread for the flu, right? After on day 0, the initial number of students infected are about 5 students. 3 days later, you've got a rate of 25 more students being infected per day. That's a pretty quick, fast spreading flu there. All right, approximately when is the flu spreading at its maximum rate? What is that rate? Okay, well, this was my P prime that told me the rate it was spreading at. And I want to know when that's equal to its maximum. There are ways to do this with calculus. At this point, we're not there yet. So really what I would say is for this point, we just graph that function and see when it reaches its maximum. So I'm going to share a screen where I graph that, and we'll find when the flu is spreading at its maximum rate and what that rate is. All right, so here I've plugged in the graph of my derivative, right, when I calculated my derivative. But here I really want to find out when this thing reaches a maximum. Looking at this graph, I clearly need to kind of zoom out a bit, so I'm going to zoom out. So here's my rate of infections. I can see that this particular flu seems to get very infectious very, very quickly. It peaks out up here, but then it starts to drop off and it's not nearly as infectious for whatever reason, right? So this is asking what the maximum rate of infection is and about what it is. So if I click here, hey, 3,25. It looks like that day 3 was actually the worst day we had. That's right at my peak of this graph. So the worst the flu got was at day 3 when it was spreading at a rate of 25 people per day. But then after that, it dropped off and became less infectious. All right, so after looking at the graph, we found that when the flu was spreading at its maximum rate, the answer to that was on day 3, which we already found that rate of 25 students per day. There it is. All right. Your assignment is 4.4.1. Give those ones a try. Stop by my office hour if you have questions. I'd be more than happy to help.